The Graphics Interchange Format is a bitmap image format that was introduced by CompuServe in 1987 and has since come into widespread usage on the World Wide Web due to its wide support and portability. The format supports up to 8 bits per pixel for each image, allowing a single image to reference its own palette of up to 256 different colors chosen from the 24-bit RGB color space. It also supports animations and allows a separate palette of up to 256 colors for each frame. These palette limitations make the GIF format less suitable for reproducing color photographs and other images with continuous color, but it is well suited for simpler images such as graphics or logos with solid areas of color. GIF images are compressed using the Lempel-Zed-Welch lossless data compression technique to reduce the file size without degrading the visual quality. This compression technique was patented in 1985. Controversy over the licensing agreement between the software patent holder, Unisys, and CompuServe in 1994 spurred the development of the portable network graphics standard. By 2004 all the relevant patents had expired. History: CompuServe introduced the GIF format in 1987 to provide a color image format for their file downloading areas, replacing their earlier run-length encoding format, which was black and white only. GIF became popular because it used LZW data compression, which was more efficient than the run-length encoding that formats such as PCX and MacPaint used, and fairly large images could therefore be downloaded in a reasonably short time, even with very slow modems. The original version of the GIF format was called 87A. In 1989, CompuServe released an enhanced version, called 89A, which added support for animation delays, transparent background colors, and storage of application-specific metadata. The 89A specification also supports incorporating text labels as text, but as there is little control over display fonts, this feature is not widely used. The two versions can be distinguished by looking at the first 6 bytes of the file, which, when interpreted as ASCII, read GIF 87A, and GIF 89A, respectively. GIF was one of the first two image formats commonly used on websites, the other being the black and white XBM. The feature of storing multiple images in one file, accompanied by control data, is used extensively on the web to produce simple animations. The optional interlacing feature, which stores image scan lines out of order in such a fashion that even a partially downloaded image was somewhat recognizable, also helped GIF's popularity, as a user could abort the download if it was not what was required. As a noun, the word GIF is found in the newer editions of many dictionaries. In 2012, the American wing of the Oxford University Press recognized GIF as a verb as well, meaning to create a GIF file, as in GIFing was perfect medium for sharing scenes from the Summer Olympics. The press's lexicographers voted it their word of the year, saying that GIFs have evolved into a tool with serious applications including research and journalism. In May 2015 Facebook added GIF support after originally rejecting support. Pronunciation: the creators of the format pronounced GIF as GIF with a soft G as in gin. Steve Willight says that the intended pronunciation deliberately echoes the American peanut butter brand, Jif, and CompuServe employees would often say choosy developers choose GIF, spoofing this brand's television commercials. An alternative pronunciation with a hard G is in widespread usage. The American Heritage Dictionary cites both, acknowledging GIF as the primary pronunciation, while the OED and the Cambridge Dictionary of American English offer only the hard G pronunciation. Merriam-Webster's Collegiate Dictionary cites both pronunciations, but places GIF in the default position. The New Oxford American Dictionary gives only GIF in its second edition but updated it to GIF in its third edition. The disagreement over the pronunciation led to heated internet debate. On the occasion of receiving a Lifetime Achievement Award at the 2013 Webby Awards ceremony, Willight rejected the alternative pronunciation, and his speech led to 17,000 posts on Twitter and 50 news articles. The White House and TV program Jeopardy! Also waded into the debate during 2013. Usage: GIFs are suitable for sharp-edged line art with a limited number of colors. This takes advantage of the format's lossless compression, which favors flat areas of uniform color with well-defined edges. GIFs may be used to store low-color sprite data for games. GIFs can be used for small animations and low-resolution film clips. File format. Conceptually, a GIF file describes a fixed-sized graphical area populated with 0 or more images. Many GIF files have a single image that fills the entire logical screen. Others divide the logical screen into separate sub-images. The images may also function as animation frames in an animated GIF file, but again these need not fill the entire logical screen. GIF files start with a fixed-length header giving the version, followed by a fixed-length logical screen descriptor giving the size and other characteristics of the logical screen. The screen descriptor may also specify the presence and size of a global color table, which follows next if present. Thereafter, the file is divided into segments, each introduced by a 1-byte sentinel, an image, an extension block, the trailer, which should be the last byte of the file. An image starts with a fixed-length image descriptor, which may specify the presence and size of a local color table. The image data follows, 1 byte giving the bit width of the unencoded symbols, followed by a linked list of subblocks containing the LZW encoded data. Extension blocks consist of the sentinel, an additional byte specifying the type of extension, and a linked list of subblocks with the extension data. Extension blocks that modify an image must immediately precede the segment with the image they refer to. The linked lists used by the image data and the extension blocks consist of series of subblocks, each subblock beginning with a byte giving the number of subsequent data bytes in the subblock. The series of subblocks is terminated by an empty subblock. This structure allows the file to be parsed even if not all parts are understood. A GIF marked 87A may contain extension blocks. The intent is that a decoder can read and display the file without the features covered in extensions it does not understand. The full detail of the file format is covered in the GIF specification. Palettes. GIF is palette-based. The colors used in an image in the file have their RGB values defined in a palette table that can hold up to 256 entries, and the data for the image refer to the colors by their indices in the palette table. The color definitions in the palette can be drawn from a color space of millions of shades, but the maximum number of colors a frame can use is 256. This limitation seemed reasonable when GIF was developed because few people could afford the hardware to display more colors simultaneously. Simple graphics, line drawings, cartoons, and grayscale photographs typically need fewer than 256 colors. Each frame can designate one index as a transparent background color. Any pixel assigned this index takes on the color of the pixel in the same position from the background, which may have been determined by a previous frame of animation. Many techniques, collectively called dithering, have been developed to approximate a wider range of colors with a small color palette by using pixels of 2 or more colors to approximate in-between colors. These techniques sacrifice spatial resolution to approximate deeper color resolution. While not part of the GIF specification, dithering can of course be used in images subsequently encoded as GIF images. This is often not an ideal solution for GIF images, both because the loss of spatial resolution typically makes an image look fuzzy on the screen, and because the dithering patterns often interfere with the compressibility of the image data, working against GIF's main purpose. In the early days of graphical web browsers, graphics cards with 8-bit buffers were common, and it was fairly common to make GIF images using the IPSAF palette. This ensured predictable display, but severely limited the choice of colors. Now that 32-bit graphics cards, which support 24-bit color, are the norm, palettes can be populated with the optimum colors for individual images. A small color table may suffice for small images, and keeping the color table small allows the file to be downloaded faster. Both the 87A and 89A specifications allow color tables of 2n colors for any n from 1 through 8. Most graphics applications will read and display GIF images with any of these table sizes. but some do not support all sizes when creating images. Tables of 2, 16, and 256 colors are widely supported. True color equals. Although the GIF format is almost never used for true color images, it is possible to do so. A GIF image can include multiple image blocks, each of which can have its own 256 color palette, and the blocks can be tiled to create a complete image. Alternatively, the GIF 89 specification introduced the idea of a transparent color where each image block can include its own palette of 255 visible colors plus one transparent color. A complete image can be created by layering image blocks with the visible portion of each layer showing through the transparent portions of the layers above. To render a full-color image as a GIF, the original image must be broken down into smaller regions having no more than 255 or 256 different colors. Each of these regions is then stored as a separate image block with its own local palette, and when the image blocks are displayed together the complete, full-color image appears. For example, breaking an image into tiles of 16 by 16 pixels ensures that no tile has more than the local palette limit of 256 colors, although larger tiles may be used and similar colors merged resulting in some loss of color information. Since each image block requires its own local color table, a GIF file having lots of image blocks can be very large, limiting the usefulness of full-color GIFs. Additionally, not all GIF rendering programs handle tiled or layered images correctly. Many rendering programs interpret tiles or layers as animation frames and display them in sequence as an endless animation, with most web browsers automatically displaying the frames with a delay time of 0.1 seconds or more. Example GIF file. Microsoft's Paint program saves a small black and white image as the following GIF file. Paint does not make optimal use of the GIF format. Due to the unnecessarily large color table and symbol width, this GIF file is not an efficient representation of the 15-pixel image. Although the graphics control extension block declares color index 16 to be transparent, that index is not used in the image. The only color indexes appearing in the image data are decimal 40 and 255, which the global color table maps to black and white, respectively. Note that the hex numbers in the following tables are in little endian byte order, as the format specification prescribes. Byte hexadecimal text or hex, value meaning 0, 47 49 46, 38 39 61 GIF 89 a header, logical screen descriptor, 6, 03003, logical screen width in pixels, 8, 05005. Logical screen height in pixels, A, F7, GCT follows for 256 colors with resolution 3x 8 bits primary, B, 000, background color number 0, C, 00, default pixel aspect ratio, RGB global color table, D, 0000000, color number 0 black, 10, 80 12800. Color number 1, 85000000, color number 40 black, 30A, FFFFFF 255 255 255, color number 255 white, 30D, 21F9 graphic control extension, 30F, 044-4 bytes of GCE data follow, 310, 01, there is a transparent background color, 311, 0000, delay for animation, not used. 313, 1016, color number 16 is transparent, 314, 00, end of GCE block, 315, 2C image descriptor, 316, 0000000, NW corner position of image in logical screen, 31A, 03000500, image width and height in pixels, 31E, 00, no local color table, 31F, 088 start of image, LZW minimum code size, 320, OB11-11 bytes of LZW encoded image data follow. 321, 0051 FC1B2870 AOC 1830101, 32C, 00, and of image data, 32D, 3B GIF file terminator. Image coding equals. The image pixel data, scanned horizontally from top left, are converted by LZW encoding to codes that are then mapped into bytes for storing in the file. The pixel codes typically don't match the 8-bit size of the bytes, so the codes are packed into bytes by a little endian scheme. The least significant bit of the first code is stored in the least significant bit of the first byte, higher order bits of the code into higher order bits of the byte, spilling over into the low order bits of the next byte as necessary. Each subsequent code is stored starting at the least significant bit not already used. This byte stream is stored in the file as a series of subblocks. Each subblock has a maximum length 255 bytes and is prefixed with a byte indicating the number of data bytes in the subblock. The series of subblocks is terminated by an empty subblock. For the sample image above, the reversible mapping between 9-bit codes and bytes is shown below. A slight compression is evident. Pixel colors defined initially by 15 bytes are exactly represented by 12 code bytes including control codes. The encoding process that produces the 9-bit codes is shown below. A local string accumulates pixel color numbers from the palette, with no output action as long as the local string can be found in a code table. There is special treatment of the first 2 pixels that arrive before the table grows from its initial size by additions of strings. After each output code, the local string is initialized to the latest pixel color. Table 9-bit, string, code action, number 0000H initialize root table of 9-bit codes, palette, colors, number 255OFFH, CLR100H, N101H, 100H clear, pixel local, color palette string, black number 4028028H first pixel always to output, white number 255FF string found in table, 28FF102H always add first string to table, FF initialize local string, white number 255FFFF string not found. In table, OFFH output code for previous string, FFFF103H add latest string to table, FF initialize local string, white number 255FFFF string found in table, black number 40FFFF28 string not found in table, 103H output code for previous string, FFFF28 104H add latest string to table, 28 initialize local string, white number 25528FF string found in table, white number 25528FFFF string not found in table, 102H output code for previous string, 28FFFF105H add latest string to table, FF initialize local string, white number 255FFFF string found in table, white number 255FFFFF string not found in table, 103H output code for previous string, FFFFF106H add latest string to table, FF initialize local string, white number 255FFFF string found in table, white number 255FFFF. FF string found in table, white number 255FFFFFFF string not found in table, 106H output code for previous string, FFFFFFF107H add latest string to table, FF initialize local string, white number 255FFFF string found in table, white number 255FFFFF string found in table, white number 255FFFFFF string found in table, no more pixels, 107H output code for last string, 101. H end. For clarity, the table is shown above as being built of strings of increasing length. That scheme can function, but the table consumes an unpredictable amount of memory. Memory can be saved in practice by noting that each new string to be stored consists of a previously stored string augmented by one character. It is economical to store at each address only 2 words, an existing address and 1 character. The LZW algorithm requires a search of the table for each pixel. A linear search through up to 4096 addresses would make the coding slow. In practice, the codes can be stored in order of numerical value. This allows each search to be done via SAR, with only 12 magnitude comparisons. For this efficiency, an extra table is needed to convert between codes and actual memory addresses. The extra table upkeeping is needed only when a new code is stored which happens at much less than pixel rate. Image decoding decoding begins by mapping the stored bytes back to 9-bit codes. These are decoded to recover the pixel colors as shown below. A table identical to the one used in the encoder is built by adding strings by this rule. Is incoming code found in table? Yes, add string for local code followed by first byte of string for incoming code, no, add string for local code followed by copy of its own first byte. Shift, 9-bit local table pixel, code, string palette color action, 100H000H number 0 initialize root table of 9-bit codes, palette, colors, OFFH number 255, 100H CLR, 101H end, 028H number 40 black decode first pixel, OFFH 028H incoming code found in table, number 255 white, output string from table, 102H28FF add to table, 103H0FFH incoming code not found in table. 103HFFFF add to table, output string from table, number 255 white, number 255 white, 102H103H incoming code found in table, output string from table, number 40 black, number 255 white, 104HFFFF28, add to table, 103H102H incoming code found in table, output string from table, number 255 white, number 255 white, 105H28FFFF add to table, 106H103H incoming code not found in table, 106HFFFFF add to table, output string from table, number 255 white, number 255 white, number 255 white, 107H106H incoming code not found in table, 107HFFFFFFF add to table, output string from table, number 255 white, number 255 white, number 255 white, number 255 white, 101H end. LZW code lengths shorter code lengths can be used for palettes smaller than the 256 colors in the example. If the palette is only 64 colors, the symbols can range from 0 to 63, and the symbol width can be taken to be 6 bits, with code starting at 7 bits. In fact, the symbol width need not match the palette size, as long as the values decoded are always less than the number of colors in the palette. The symbols can be any width from 2 to 8, and the palette size any power of 2 from 2 to 256. For example, if only the first 4 colors of the palette are used, the symbols can taken to be 2 bits wide with code starting at 3 bits. Conversely, the symbol width could be set at 8, even if only values 0 and 1 are used. These data would only require a 2-color table. Although there would be no point in encoding the file that way, something similar typically happens for B-color images. The minimum symbol width is 2, even if only values 0 and 1 are used. The code table initially contains codes that are 1 bit longer than the symbol size in order to accommodate the 2 special codes CLR and end and codes for strings that are added during the process. When the table is full, the code length increases to give space for more strings, up to a maximum code 4095 equals FFF, hex. As the decoder builds its table, it tracks these increases in code length and it is able to unpack incoming bytes accordingly. Uncompressed GIF equals. The GIF encoding process can be modified to create a file without LZW compression that is still viewable as a GIF image. This technique was introduced originally as a way to avoid patent infringement. Uncompressed GIF can also be a useful intermediate format for a graphics programmer because individual pixels are accessible for reading or painting. An uncompressed GIF file can be converted to an ordinary GIF file simply by passing it through an image editor. The modified encoding method ignores building the LZW table and emits only the root palette codes and the codes for clear and STOP. This yields a simpler encoding but sacrifices all of the compression. Each pixel in the image generates an output code indicating its color index. When processing an uncompressed GIF, a standard GIF decoder will not be prevented from writing strings to its dictionary table, but the code width must never increase since that triggers a different packing of bits to bytes. If the symbol width is n, the codes of width n+1 fall naturally into two blocks, the lower block of two encodes for coding single symbols, and the upper block of two encodes that will be used by the decoder for sequences of length greater than 1. Of that upper block, the first two codes are already taken, 2n for clear and 2n+1 for stop. The decoder must also be prevented from using the last code in the upper block, 2n+1 or 1, because when the decoder fills that slot, it will increase the code width. Thus in the upper block there are two NA3 codes available to the decoder that won't trigger an increase in code width. Because the decoder is always one step behind in maintaining the table, it does not generate a table entry upon receiving the first code from the encoder, but will generate one for each succeeding code. Thus the encoder can generate two NA2 codes without triggering an increase in code width. Therefore the encoder must emit extra clear codes at intervals of 2 NA2 codes or less to make the decoder reset the coding dictionary. The GIF standard allows such extra clear codes to be inserted in the image data at any time. The composite data stream is partitioned into subblocks that each carry from 1 to 255 bytes. For the sample 3x5 image above, the following 9-bit codes represent clear followed by image pixels in scan order and stop. 9-bit codes: 1000280 FFO 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 280 FFO 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 FF101. After the above codes are mapped to bytes, the uncompressed file differs from the compressed file thus. 320, 14 2020 bytes uncompressed image data follow. 321, 0051 FCF BF70 FC5 BF7 FFF AFDF BF7 EFDF BF7 F0101, 335, 00, end. Compression example: the trivial example of a large image of solid color demonstrates the variable length LZW compression used in GIF files. The code values shown are packed into bytes which are then packed into blocks of up to 255 bytes. A block of image data begins with a byte that declares the number of bytes to follow. The last block of data for an image is marked by a 0 block length byte. Interlacing: the GIF specification allows each image within the logical screen of a GIF file to specify that it is interlaced. That is, that the order of the raster lines in its data block is not sequential. This allows a partial display of the image that can be recognized before the full image is painted. An interlaced image is divided from top to bottom into strips 8 pixels high, and the rows of the image are presented in the following order: pass 1, line 0 from each strip. Pass 2, line 4 from each strip. Pass 3, lines 2 and 6 from each strip. Pass 4, lines 1, 3, 5, and 7 from each strip. The pixels within each line are not interlaced, but presented consecutively from left to right. As with non-interlaced images, there is no break between the data for one line and the data for the next. The indicator that an image is interlaced is a bit set in the image's header block. Animated GIF. Basic animation was added to the GIF 89 spec via the graphics control extension, which allows various images in the file to be painted with time delays. An animated GIF file comprises a number of frames that are displayed in succession, each introduced by its own GCE, which gives the time delay to wait after the frame is drawn. Global information at the start of the file applies by default to all frames. The data is stream-oriented, so the file offset of the start of each GCE depends on the length of preceding data. Within each frame the LZW-coded image data is arranged in subblocks of up to 255 bytes. The size of each subblock is declared by the byte that precedes it. By default, however, an animation displays the sequence of frames only once, stopping when the last frame is displayed. Since GIF is designed to allow users to define new blocks, Netscape in the 1990s used the application extension block to implement the Netscape application block. This block, placed immediately before all the animation frames, specifies the number of times the sequence of frames should be played. Support for these repeating animations first appeared in Netscape Navigator version 2.0, and then spread to other browsers. Most browsers now recognize and support NAB, though it is not strictly part of the GIF 89 specification. The following example shows the structure of the animation file rotating Earth GIF shown at the top of the article. Byte hexadecimal text or hex, value meaning 0, 47 49 46, 38 39 61 GIF 89 a header, logical screen descriptor, 6, 90 01 400, width in pixels, 8, 90 01 400, height in pixels, A, F7, GCT follows for 256 colors with resolution 3x 8 bits primary, B, 000, background color number 0, C, 00, default pixel aspect ratio, D, global color table, 30D, 21FF application extension block, 30F, OB11, 11 bytes of data follow. 310, 4E 4554, 534341, 5045 Netscape 8-character application name, 322E 32.0, application authentication code, 31B, 033, 3 more bytes of data, 31C, 011, data sub-block index, 31D, FFFF 65535, unsigned number of repetitions, 31F, 00, and of app extension block, 320, 21F9 graphic control extension for frame number 1, 322. 044, 4 bytes of data follow, 323, 08, bit fields 3x, 311, 0001000 restore to BG color, 324, 0900-0.09 seconds delay before painting next frame, 326, 00, no transparent color, 327, 00, end of GCE block, 328, 2C image descriptor, 329, 0000000, NW corner of frame at 0, 0, 32. D, 9001-9001, frame width and height, 400 x 400, 331, 00, no local color table. No interlace, 332, 088 LZW min code size, 333, FF 255-255 bytes of LZW encoded image data follow, 334, data, 433, FF 255-255 bytes of LZW encoded image data follow, data, 92BA, 00, and of LZW data for this frame, 92BB, 21F9 graphic control extension for frame number 2, 153B7B, 21F9 graphic control extension. For frame number 44, 15CF353B file terminator. The animation delay for each frame is specified in the GCE in hundredths of a second. Some economy of data is possible where a frame need only rewrite a portion of the pixels of the display, because the image descriptor can define a smaller rectangle to be rescanned instead of the whole image. Displays that do not support animated GIFs show only the first frame. Internet Explorer slows down GIFs if the frame rate is 20 frames per second or higher, and Microsoft reports that Google Chrome and Safari also slow down some GIF animations. Unisys and LZW patent enforcement. In 1977 and 1978, Jacob Ziv and Abraham Lempel published a pair of papers on a new class of lossless data compression algorithms, now collectively referred to as LZ77 and LZ78. In 1983, Terry Welch developed a fast variant of LZ78 which was named Lempela Ziva Welch. Welch filed a patent application for the LZW method in June 1983. The resulting patent, US 4,558,302, granted in December 1985, was assigned to Sperry Corporation, who subsequently merged with Burroughs Corporation in 1986 and formed Unisys. Further patents were obtained in the United Kingdom, France, Germany, Italy, Japan and Canada. In June 1984, an article by Welch was published in the IEEE magazine which publicly described the LZW technique for the first time. LZW became a popular data compression technique and, when the patent was granted, Unisys entered into licensing agreements with over 100 companies. The popularity of LZW led CompuServe to choose it as the compression technique for their GIF format, developed in 1987. At the time, CompuServe was not aware of the patent. Unisys became aware that the GIF format used the LZW compression technique and entered into licensing negotiations with CompuServe in January 1993. The subsequent agreement was announced on December 24, 1994. Unisys stated that they expected all major commercial online information services companies employing the LZW patent to license the technology from Unisys at a reasonable rate, but that they would not require licensing, or fees to be paid, for non-commercial, non-profit GIF-based applications, including those for use on the online services. Following this announcement, there was widespread condemnation of CompuServe and Unisys, and many software developers threatened to stop using the GIF format. The PNG format was developed in 1995 as an intended replacement. However, obtaining support from the makers of web browsers and other software for the PNG format proved difficult and it was not possible to replace the GIF format, although PNG has gradually increased in popularity. Therefore, GIF variations without LZW compression were developed. For instance, the LibGIF library, based on Eric S. Raymond's GIFlib, allows creation of GIFs that followed the data format but avoided the compression features, thus avoiding use of the Unisys LZW patent. A 2001 Dr. Dobbs article described another alternative to LZW compression, based on square roots. In August 1999, Unisys changed the details of their licensing practice, announcing the option for owners of certain non-commercial and private websites to obtain licenses on payment of a one-time license fee of $5,000 or $7,500. Such licenses were not required for website owners or other GIF users who had used licensed software to generate GIFs. Nevertheless, Unisys was subjected to thousands of online attacks and abusive emails from users believing that they were going to be charged $5,000 or sued for using GIFs on their websites. Despite giving free licenses to hundreds of non-profit organizations, schools and governments, Unisys was completely unable to generate any good publicity and continued to be condemned by individuals and organizations such as the League for Programming Freedom, who started the Burn All GIFs campaign in 1999. The United States LZW patent expired on June 20, 2003. The counterpart patents in the United Kingdom, France, Germany and Italy expired on June 18, 2004. The Japanese counterpart patents expired on June 20, 2004, and the counterpart Canadian patent expired on July 7, 2004. Consequently, while Unisys has further patents and patent applications relating to improvements to the LZW technique, the GIF format may now be used freely. Alternatives =PNG Portable Network Graphics was designed as a replacement for the GIF format in order to avoid infringement of Unisys' patent on the LZW compression technique. PNG offers better compression and more features than GIF, animation being the only significant exception. PNG is more suitable than GIF in instances where true color imaging and alpha transparency are required. Although support for PNG format came slowly, new web browsers generally support PNG. Older versions of Internet Explorer do not support all features of PNG. Versions 6 and earlier do not support alpha channel transparency without using Microsoft-specific HTML extensions. Gamma correction of PNG images was not supported before version 8, and the display of these images in earlier versions may have the wrong tint. PNG files can be much larger than GIF files in situations where a GIF and a PNG file were created from the same high-quality image source, as PNG is capable of storing more color depth and transparency information than GIF. However, for identical 8-bit image data, PNG files are typically smaller than the equivalent GIFs, due to the more efficient compression techniques used in PNG encoding. Complete support for the GIF format is complicated chiefly by the complex canvas structure it allows, though this is what enables the compact animation features. Animation formats MNG was originally developed as a PNG-based solution for animations. MNG reached version 1.0 in 2001, but few applications support it. In 2006, an extension to the PNG format called APNG was proposed as alternative to the MNG format by Mozilla. APNG provide the ability to animate PNG files, while retaining backwards compatibility in decoders that cannot understand the animation chunk. Older decoders will simply render the first frame of the animation. The PNG group officially rejected APNG as an official extension on April 20, 2007. There have been several subsequent proposals for a simple animated graphics format based on PNG using several different approaches. Nevertheless, animated portable network graphics is still under development by Mozilla and is supported in Firefox 3 while MNG support was dropped. Embedded Adobe Flash objects and MPEGs are used on some websites to display simple video, but require the use of an additional browser plugin. WebM and WebP are in development and are supported by some web browsers. Other options for web animation include serving individual frames using AJAX, or animating SVG images using JavaScript or SMIL. With the introduction of widespread support of the HTML5 tag in most web browsers, some websites use a looped version of the video tag generated by JavaScript functions. This gives the appearance of a GIF, but with the size and speed advantages of compressed video. A notable example is Imgur and their GIF meta format, which is really a video tag playing a looped MP4 or WebM compressed video. See also: comparison of graphics file formats, comparison of layout engines, GNU plot utils, software patent, GIF art, a form of digital art associated with GIF format, Microsoft GIF Animator, a free program to create simple animated GIFs, Cinematograph, a partially animated photograph often in GIF format. References. External links: Spec GIF 8980XT GIF 89, a specification on w3.org, LZW and GIF Explained, Animated GIFs, a 6-minute documentary produced by Offbook.